Hello.
Hello, guys. Okay, so this is the special session. This is an ending keynote, and we ask Michael, the author of amazing book, The Art of Immutable Architecture, which I recommend everyone to read, to give that final session. And this session will be in English, and this is the only English session in the whole during the whole conference. But if you wish to ask any questions, don't worry, you can write them in Polish. We will translate them. However, during the last session, we will give the voice to Michael, and Michael will say a bit more words about himself and what he's doing. Hi, Michael.
Hey, how do you do? Very good to be here.
Thank you for accepting our invite for this conference, which was really, we had an idea and we just materialized it. Basically, we didn't materialize it. Piotr started to write to everyone, say, okay, I've got all of the speakers. We need website and we're missing architecture. I was like, okay, we're missing the architecture part of architecture and containers. So I started. Yeah, I was reading this amazing book recently. I will write to Michael and see if he will agree. And thank you for that. Thank you for accepting. I'm really glad you did it. Before we start, there's only one information. We have a charity for our friends.
Godson.
What?
Godson.
Godson. All right. Yes. So if you will click that link, it's /pomagamy. Architektura in Kontenery.pl. Whenever it will lead to a page Się Pomaga, where you can donate for David some of the money, even the small amount. I'm saying that we will be grateful. This is to help a kid with cancer. And without the further ado, Michael, I'm giving you a voice. Could you introduce yourself and tell more about yourself to listeners?
Indeed, thank you very much, and thank you everyone for hanging out with us today and learning all about containers, architecture, and what we can do to build better software. I'm Michael L. Perry. I am a principal consultant at a company in the United States called Improving, and recently promoted to technical director at Improving, and author of The Art of Immutable Architecture. I'm also a Pluralsight author, so you may have seen some of my courses on cryptography and on architecture. I've got one out there just recently refreshed on building distributed systems. So I love helping people to apply theory in order to bring good architectures to practice, and so that's why I love to study mathematics and see how we can bring that to life in software.
Okay, Michael. So the stage is yours.
All right.
Thank
you so much. All right, appreciate it. All right. So again, thank you all for joining this wonderful day, and I wanted to kind of round things out as we were learning all about Kubernetes and about containers. Okay, so we've got this great tool, and now what do we do with it? And so I wanted to share with you some of the things that I've learned about building architectures on distributed platforms like a Kubernetes cluster, and talk about some of the hard problems that emerge and some of the solutions that I've discovered by researching mathematics and that I've assembled in The Art of Immutable Architecture. So it kind of starts out, if you talk about Kubernetes these days, you'll hear it kind of as the punchline of a joke. In fact, that Dilbert cartoon right there at the top, that was one that my product owner shared with the team when we were talking about solving a problem using Kubernetes. And he's like, "Oh, I know that word. It's the punchline to a joke." And the joke is that Kubernetes is such a powerful tool that it just seems to be the hammer that we bring out in order to solve difficult problems. So the joke is really on the success of Kubernetes as being a really powerful platform. And so you might think that with all of these memes, that all of the problems have been solved. And there, in fact, are some really problems remaining that Kubernetes itself does not have a solution for. And those are the problems that I want to address. But to kind of set the stage, let's go back. It used to be that the solution that people would reach for was virtual machines, and virtual machines are still a very powerful part of the solution. But with a virtual machine, you had these virtual adapters, and you had to map them to physical adapters and set up your routing tables, and there was a lot of management related to those virtual machines. And so they brought a solution, but then they also brought their own set of problems. And then along comes Docker, and we've got containers. And so now we're no longer managing those individual machines. We're no longer investing in a VM. A container is not an investment. A container is not something that you manage and update. It's something that you destroy, and then you create a brand new one. There was still a bit of management to set up those networks and to make sure that certain containers had access to other services within other containers, and so the problem wasn't completely solved. And then along comes Kubernetes, and so with Kubernetes now, you can map the services to a just kind of a name, and then within that cluster, any pod that offers a service using that name, those tags, gets mapped to that port, and things just kind of get wired up for you automatically. So now you can just create new instances of these pods. You scale them up, scale them down, and there's a lot of management that's taken care of for you. So you would think that going from virtual machines, all the way to Kubernetes, that we have solved all of the problems. In fact, the problem that we have solved along the way is strictly a topology problem. So topology is all about what can connect to what. What is the shape of our solution? But that still leaves us with a consistency problem. And the consistency problem is all about the data that's running within this cluster. And so I want to take a look at a typical Kubernetes cluster, and let's really investigate this consistency problem, and let's see where this comes from. So we'll start by looking at a Kubernetes cluster. It's made up of containers running within pods. And then in order to scale and have multiple pods, we'll put those into a deployment, right? And so each of these pods are running the same workload. And so because they're running the same workload, we can access that service on any of these pods. And so in order to do that, we put a service in front of them, and now all of these pods are receiving messages on this particular port, and the service is load balancing among all of them. So right now, it doesn't matter which of the pods the service sends the request to, because they're all stateless and they're all running the same workload. So they're all going to produce the same result. But not all of our applications can be completely stateless. Sometimes we need to actually remember some data from one request to the next. And so we're going to put some volumes into our architecture here, and we're going to map those to the pods. And now we're not talking about a deployment anymore. We're talking about a stateful set. And so now, rather than deploying a stateless application to those pods, we're deploying something that's stateful, that needs to record information. And that changes fundamentally the relationship between that service and the various pods. Because if that service routes a request to the first pod, it stores some object in that first volume. And now it matters. It would be a different experience to route the next request to a different pod because they have different information. And so what this service needs to do is to replicate that information onto all of the different volumes so that it doesn't matter anymore which one gets the request. And so a lot of the workloads that we'll deploy in this way will set up a different service, something kind of in the back end that it uses to talk to one another. So this might be Postgres, and it's running a replication service in the back end and replicating data from one set of tables to another. Or this might be Elasticsearch, and each of these would be a different node within the Elasticsearch cluster, and it's got a back channel that is using to synchronize those nodes. So now we've got several different volumes, and each one through this replication mechanism is representing the same exact set of data. And not only are these objects the same objects conceptually, but they're also in the same format. These are all Postgres tables. These are all Elasticsearch indexes. And so we're letting the thing that knows about that format, Postgres, Elasticsearch, run this replication for us. So we usually build our applications out of combinations of these things. So on the front end, we'll have some stateless services that are inside of our web cluster, and then when they need to access an API in the back end and get some data, then they'll access a database cluster in the back end that's maybe running Postgres and keeping those volumes in sync. And so if we have something that's just this size, now we can rely upon Postgres to do that replication for us, and it solves the consistency problem. But we don't often stop here. We will sometimes have to add more services to our microservices architecture. So, for example, we might add a search cluster. So we've got Postgres running in the database cluster, Elasticsearch in the search cluster, and we want to make sure that whenever we put an object into the database, that object is also represented in search. So somebody can use the application, manage some objects, and then they get replicated to the back end. Now, the unfortunate part about this is that these are in two completely different formats now. So whereas in the database cluster, we've got those in a Postgres file format. On the backend, those are in Elasticsearch indexes. And so the same pattern doesn't work. We can't just use replication in order to replicate Postgres data into Elasticsearch data. And so whenever somebody adds a new object to the database, we want to index that object in the search engine, but there's no solution that comes out of the box to do that. That's something that we need to build ourselves. Now, we have some tools to help us out. So, for example, we can put some queues in place. We can set up Kafka. We can use an event store. So we've got different topology that we can deploy to our Kubernetes cluster in order to help us to move that object from the front end into the back end and translate it from one format to another. But that is still something that we have to manage ourselves. We have to define for the system, what does it mean for an object that's in a database to be represented in a Kubernetes or in a Elasticsearch index? We have to do that mapping, and we have to do that translation work. And so, whereas Kubernetes and all of the services that we can deploy will take care of topology problems for us, they still leave these consistency problems between different services up to us to solve. They give us some help, but they don't completely solve the problem. And so that's where I think we need to consider a new way of thinking. So rather than thinking in terms of all of these different workloads and all these different volumes that are running out there. Let's take that topology. Let's keep that to one side, and let's talk about the data as something completely divorced from topology. And let's see if we can find something in the world that that already works like that, and maybe we can adopt some of those ideas. Well, as it so happens, you're probably already very familiar with something that does work like that, and that would be Git. So in Git, you would have different developers. They're all working on their own repositories with their own working branches, and then they share their commits by pushing them to a remote repository in a main branch. And so in this scenario, you've got a developer working on working branch 2 and another one in working branch 3, and they each create commits. So they might create them at exactly the same time. There might be some time between them. It doesn't matter which one actually came first. It's just that each one was created without knowledge of the other. And so then at some point they both push to the remote, so that they're now lined up within the main branch. And now that they get lined up, the order does matter. So now within Git, it knows that these things happen in a particular sequence. And then at this point, the developers will pull. And so each developer will see the commits that they have not yet seen, and they will be added to their working branches. For most of the developers, those commits will come back down in the same order that they were pushed. But for some developers, they'll come down in a different order. And remember, in commits, in Git, order matters. So it's important for the developers to pull this branch down and put it into the correct order. So sometimes things that they haven't seen yet actually happen earlier in history. And so in Git, we've got a feature to do this called rebase. So we'll pull and we'll rebase our changes on top of the main branch. And then everybody sees all of the different commits in the same order, which is how Git guarantees that they will all converge to the same outcome. They will all see the same source code. So this is a good starting point for a model of how we can architect our applications, but it also reveals some of the problems. So let's take a closer look at that series of commits that occurred within that main branch. So if we look closely at those, we'll see that sometimes people are changing the same things, and sometimes they're changing things that are completely unrelated within the source code. So sometimes order matters, and sometimes it doesn't. And so if we were able to draw an arrow from a commit to the predecessor commits that definitely had to come before, then we could set up a graph of these dependencies. These are the places where order matters. So let's just grab that graph at the front, shake it, let all of the successors flow down, and now we've got a directed acyclic graph where all of these dependencies are pointing up. We can say that these arrows point back to the past. These are the predecessors, the things that necessarily came before, and then the tails of those arrows fall down to the successors, the things that come later. And if we were able to represent our application as a directed acyclic graph, then we could solve this problem of things happening out of order. And so a set of patterns that I like to use in order to accomplish this is what I call a historical model. So this is a typical example of a historical model. It's a directed acyclic graph of historical facts. So a historical fact is a decision that somebody has made. And that decision is immutable. You don't go back and change the decision in the past. You just make new decisions in the future. And this relationship of of these past decisions and how they evolve into future decisions, that is how your application evolves over time to represent more and more up-to-date information. So in this example here, we've got an application where 3 different kinds of people are collaborating. You've got conference organizers, and those conference organizers are making certain decisions. And then you have speakers that want to present their presentations at the conference. And then you've got the attendees at the conference. And each of these roles, each of these types of people are making certain decisions. So to start things out, the conference organizer makes the decision to host a conference. And then following that decision, they send out a call for speakers. So this is now an invitation for people to submit their abstracts for their talks. A speaker, on the other hand, makes the decision to identify themselves as a speaker, first of all, and then to write an abstract. So this would be a title, some description of the talk that they want to present. And so far, these 2 sets of decisions have nothing to do with one another. A speaker could have written abstracts in the past before even seeing a call for speakers for this particular conference, or they might write the abstract in response to the call for speakers. So the order is completely up to them. There's nothing about those decisions themselves that capture that order. And so that's represented by not having any arrows that go from abstract to call for speakers or vice versa. Instead, you've got the proposal, which comes after both of those. So the proposal is the first opportunity that the speaker and the organizer have to connect. That's the first decision, in this case made by the speaker, that depends upon a prior decision by an organizer. So if you were to peer into each of these different ellipses and see what does this decision look like, you could just look inside of it and see a JSON object, or some document, some object structure. So a conference that could just be a JSON object that says, okay, we're going to on this date in this place have a conference called Architecture and Containers, and that would just be a document that represents that conference. And then the call for speakers is instructions about how to submit your proposals, and specifically how to submit your proposals for this conference. So the call for speakers actually includes the conference. One way that you could represent that is to take that conference JSON object and actually put it inside of the call for speakers JSON object. And so now it just becomes a larger object. And so you can think about each of these different decisions as its own separate data structure, and the predecessor relationships between these decisions are just encapsulating those objects within one another. So after the speaker makes their proposal, then the organizer receives that proposal and can accept or reject, and the story continues from there. And so you can build up the current state of an application by taking a look at any one of these decisions and then looking at what successors have taken place since then. And so that's the process of historical modeling. So what could a historical model represent? One thing that it could represent are stages within a workflow. We saw a slightly complicated interconnected workflow. It's a collaboration between a conference organizer and speakers. Here's another workflow that you might come in contact with, and that is somebody placing an order and then receiving an invoice for that order. So, so the order object, you could think of that as a JSON object that has several different items in it that you want to purchase, and then you submit that order, and then the company responds with an invoice. It says, okay, for this order of all these different items, I will invoice you with these terms, with this price. You send your payment here, and then you respond with a payment. So the payment now is another JSON object, which is saying, okay, here's the form of payment. Here's here's the date on which I'm paying it. I'm paying this particular invoice, and it continues down from there. In a lot of applications, we will represent this kind of a workflow with a state machine, where your order will be placed, and then once it's invoiced, it's going to be in the invoiced state, and then payment is received, and that transitions you to the payment state or paid state. Then you're going to have these loops that go back to, okay, it was refunded, so it's no longer paid. The payment has been returned, or it's been canceled. So now you've gone into the canceled state. You have to do all these compensating transactions to refund the payment or to return the items, and you're trying to keep track of what has happened by what state you're currently in. If instead you just simply capture each of the different historical facts as an immutable object, then you can just look at what facts are present, what facts are absent, and you'll know what the current state is. Meanwhile, as you progress from one state to the next, you're capturing more information. So when you insert the invoice, you're capturing the terms, you're capturing the invoice number, you're capturing the total. When you insert the payment, you're capturing the form of payment. You're capturing the date of that payment. And so this extra information is necessary in order to understand how to proceed. So why not go ahead and capture that in the same immutable object that is moving your state forward? And so that's what a historical model can do to transform a state machine into these immutable stages of a workflow. Now, not all of our applications are workflow-based. Some of them have entities with properties. So, for example, within the same system, we'll have customers, and customers will have a shipping address. So the entity at the top, that might be your customer entity. It's maybe just a JSON object that just has customer ID. And then the entity property 1, that's their shipping address. Now, at some point, they change locations, and so they enter a different shipping address. So now they've got entity property 2 that points back to entity property 1. So it's a new shipping address that replaces the previous one. So at this point, if you were to ship something to them, you would not want to ship it to entity property 1 anymore. You wouldn't want to ship it to the first address. You would want to ship it to the second address. But then they change locations again, and now they're replacing the second one with the third. So each one of these properties refers back to the entity. So it's saying, this is the shipping address of this particular customer. But it's also referring back to the previous shipping address. What was that property before? What am I changing it from? And so by keeping track of what you're changing it from and what you're changing it to, you can see, just by looking at this graph, what is their current address. And that's the important information that you're trying to glean from this graph. Now, so far, we've been talking about these graphs completely divorced of topology. We haven't talked about how we're deploying these graphs to different machines. So now let's let topology kind of leak into the conversation a little bit, and let's suppose that you've got the same customer accessing the system from 2 different machines, and so they're finding their way through 2 different routes into the database. And so so far we've seen them perform sequential edits on their shipping address. Now let's suppose that they make a concurrent edit on their shipping address. So from one machine, they make a change, and from another machine, they make a different change. If we just simply let the system capture those changes as immutable facts, then we'll end up with a graph that looks like this. So we'll see that for this entity, for this customer, we will have the address 2 and the address 3, both of which were created with prior knowledge of address 1, but with no knowledge of each other. And so because we're capturing the information in that way, then we can just look at the graph and we can see, okay, this first one, it has only one leaf. Therefore, entity property 3 represents their current shipping address. The second graph has 2 leaves. So I can't tell just by looking at the graph which one is the correct shipping address. There's not enough information in the system to do that. And so what we're really doing when we constrain ourselves to having these immutable facts with the predecessor relationships is we are making sure that the system doesn't enforce any constraints that it doesn't have the information to do. So we are allowing the system to represent the fact that there was a concurrent edit. There could be one of 2 different possible shipping addresses. But the system doesn't just leave us hanging like that. We can resolve the conflict. So if somebody were to now take a look at this graph and see, okay, there are 2 concurrent edits, there are 2 leaves of this tree, then that person could say, okay, I'm going to create a new shipping address. Maybe it's exactly the same value as shipping address 2 or shipping address 3, but this is a completely new fact, a completely new decision that they made that replaces both of those. And it says, nope, the correct shipping address for this customer is entity property 4. So if you are familiar with Git and you have used Git in order to solve these kinds of problems, then this might look familiar to you. So when we are talking about these concurrent edits, we've got 2 different developers working on their own branches, making independent changes. You end up with a system that has 2 possible outcomes, 2 different branches. And then you want to resolve that conflict, and so you perform a merge. A merge in Git is simply a commit that has more than one predecessor. It has 2 parents. And so we're using the same idea, but now not on our source code, but on our objects. And that is how we can represent things that happen concurrently within a distributed system. So this is still completely divorced from topology. That means that I can take this graph of concurrent edits and I can share that among all of the different system, nodes within the system, and they'll all understand that there were concurrent edits. I can take this conflict resolution, apply it at one node, and then propagate it to all the others, and now everybody will understand that the conflict has been resolved. So we are still keeping topology and our data, our consistency, separate, but we're allowing the fact that topology changes to help us constrain our data to make that possible and to represent that in a meaningful way. So we've talked about workflows, we've talked about properties. Let's talk about deletion. So when I say immutable records, I mean the records themselves can't be modified. I also mean that those records can't be deleted. They can't be removed from the system. So how do I represent deletion within an immutable model? So in this model here, we've got a company that is in the process of placing an order. And so they're going to add order lines to that order. So this is like their shopping cart experience. And then they decide that they want to remove an order line from their shopping cart. They can't delete that order line fact. They can't unmake that decision. that's already been shared with other machines, and you can't reach out into the network and claw that decision back. So instead, you just insert another successor. You follow that up with a new decision called an order line deletion. So now that order line no longer exists. It's no longer in the order. Well, but it does exist. I can see it right here in the graph. So what you want to do when you show that shopping cart to the consumer is you want to run this graph through a projection. You want to show me all of the order lines such that there does not exist an order line deletion. So you run it through that projection, and now order line 2 appears on the user interface, but order line 1 does not. So so it's all about taking this graph of immutable facts and then projecting it back to the user in such a way that it appears to them as if something has been deleted. Now, what if they didn't intend to delete that order line? Maybe they make a mistake. Well, we can't claw back the order line deletion, so we follow that up with an order line restoration. And now we can change our projection so that we're saying, all right, show me all of the order lines for this order such that there does not exist an order line deletion, such that there does not exist an order line restoration. So you've got this chain of not exists clauses on your query. So, of course, when I show this to people, the natural thing for them to expect is, oh my goodness, what if I want to delete that order line again? Do I put another one on the bottom of that chain? Does this continue indefinitely? And the answer, thankfully, is no. You can just create a brand new order line deletion next to that first one, referring back to the same order line. You don't have to continue this chain indefinitely. In fact, a historical model tends to work out a lot better if it's wider rather than taller. So let's not have a series of related commits one after the other, but instead let's have as many of them unrelated as possible. So if we were to take our applications and model them like this, how does that help us to now bring that back to our distributed system and to build something that now we can deploy within a Kubernetes cluster? And a powerful idea within a historical model is something called a transitive closure. And that helps us to design the messages that go into our distributed systems. So, for example, let's suppose that we wanted to send somebody information about this decision right here that has the star on it. So this is my decision to submit a proposal to a conference. So in response to a call for speakers, here's my submission of this abstract. And if we were to follow that decision and all of its predecessors and all of their predecessors all the way up the graph and include everything that that we can reach from that operation, we have just performed something called the transitive closure of the predecessor operation. So this includes all of the information that was known at the time we made that decision. Now, there are other parts of the system, some other decisions that may have in fact been made earlier in time, earlier in clock time, if you were to take a look at the wall clock. But they are not in that transitive closure because they were successors of those predecessors. So any successors, anything that follows, was not necessarily known at that time. It's not included within that transitive closure. And so it's not actually part of that decision. Now, this might be important information. Like, for example, this is my proposal to this particular conference. At the time that the call for speakers was published, they were saying, okay, we're going to meet in person at this location at this time. And so that information was captured in a successor of the conference, but still not a predecessor of my proposal. So it wasn't in this transitive closure. And so that means that that information could possibly change. And so if it could change, we could have new successors, then it's not part of this message. I have to have a different message that captures that change. So one of the things that I love to do is to diagram a solution as a historical model, and then find these transitive closures, these cones that point upward in the directed acyclic graph. And then anything that falls outside of those cones, I have to design a new message for. And so from this, I will derive a series of messages that helps me to make sure that my different systems remain in sync, that they become consistent. So quick aside, for those of you that are physics geeks like I am, then you can think of this as a past light cone of a particular event in space-time. So, one way that you can think about events that are happening in space-time is that they're a single four-dimensional point, 3 dimensions of space, 1 dimension of time. The Time Lord behind me is really getting excited, and so all of the things that could have happened, that could have affected that decision, have to be somehow within this this sphere, moving at the speed of light toward this event. If something happened outside of that sphere, there's not enough time for it to have for its effect to have gotten here to affect that decision. And so I like to think of this as the past light cone of a particular event. So these are all of the decisions that could have influenced that particular decision. And so all of that information gets captured within the message. Anything outside of that past light cone has to be a new message. Okay, so we've taken our application, we've broken it down into messages, identified the people who are responsible for making those decisions, and then captured the transitive closure of those historical facts in order to define messages that then we can send from one system to another. What we can now do is bring this back to our cluster. We can talk about how do we take this database and how do we take this search index? How do we make them consistent using what we've just learned, what we've just modeled? So the objects that we were talking about in the historical model are immutable historical facts, and they are related to one another by their predecessor relationships. They know which ones had to have come before. Those objects are not rows in a database. Those objects are not objects in a search index. They need to be mapped into those different forms. So we need to somehow take that decision, that customer entity with all of the different changes to that entity's shipping address, and we have to somehow project that into records in a relational database. Now, I am in the habit of creating relational databases that only allow inserts, never updates, never deletes, and the foreign keys themselves are those predecessor relationships. But not everybody does that. And so most of the time, the application database that you're working with is going to be state-based in nature. It's going to be mutable. And so you have to take those immutable historical facts and map them into updates and inserts and, yes, deletes on that state-based database. Likewise, you need to take those immutable facts and you need to project them. You need to map them onto documents that you can put inside of your search index. And those documents in the search index need to represent the current state of the object that you're searching for. Most of the time, you're not searching based on previous data. You want to search based on what's most up to date. And so you need some mechanism that's going to translate, that's going to project from the immutable world into the mutable world. And this is now where Kubernetes comes back into the picture and has something that we can leverage. In fact, I believe that you just learned about such a system in the previous session on Dapper. So this is a way of taking not just the single container that is the main reason for running this pod, but having an additional sidecar container within that each pod. So if we were to give each of these sidecars another volume, so go ahead and mount volumes to both the main workload and the sidecar. Now that second volume could be the historical model. It could be the immutable directed acyclic graph of all of the records that we need to exchange. And so now that we are running within the same pod, that sidecar could just talk directly to the stateful application sitting right next to it, and it can translate those incoming historical facts into the insert, update, delete statement on the database, or into the update index or drop index for the search cluster. So these sidecars can speak in the immutable language and communicate with the parts of our application that were written with mutability in mind. You don't have to completely rewrite your entire application in order to adopt immutability. And then if you were to have another service that these sidecars would all communicate using, now they are using that service to exchange immutable facts. So somebody on the database, they they come in and they insert a new customer. Okay, I've got a new customer fact. That application talks to the immutable runtime, and it says, okay, new customer, puts that onto that backplane service, and then the search cluster picks that up, puts that into its immutable database, and now talks to the search service and says, all right, I need you to index this customer. Customer comes in and changes their shipping address. Now, okay, let's insert that into the immutable record, into the immutable graph, and that flows to other parts of the system as well. Here's a new product, and we're going to change the description, and now the search index is up to date with all of the different product descriptions. You've got the immutable records in one set of volumes, and then the searchable mutable records in a different set of volumes. And so this helps us to solve not just the topology problem that Kubernetes has given us a lot of great tools for, but this also helps us to solve the consistency problems. So this helps us to now express our information in a way that can be shared without having to think too much about which machine is sending and which machine is receiving. You don't have to think about the order in which these facts appear at different parts of the system. If the order matters, then there's going to be a predecessor-successor relationship between them, and that will be captured within the graph. If the order doesn't matter, then the order doesn't matter. Then there's not going to be this predecessor-successor relationship, and they can arrive in either order. And then it's just the interpretation of that graph that tells you what the current state is. A new fact arrives, it changes the graph in some way, you re-execute that interpretation, you rerun that projection into your mutable state, and then you update your search index, you update your database, you insert or delete records within your database so that your application continues to function the way that it likes to function. The historical model captures that causal information. It captures that relationship between what must have come before and what follows. And so that way our individual applications don't have to. Our applications can continue to be written using the same tools and the same patterns that that we're used to writing them. Over time, you might find, as I have, that the ideas of historical modeling and immutability start to permeate your application design, and you actually do start to write databases that only allow inserts. And so these ideas become even more powerful and even more ingrained. But you don't have to start there, and you don't always have to be there. A search over a historical model directly is going to be a pretty slow search. In order to really take advantage of the power that we've got with things like Elasticsearch, we need to project those into mutable indexes. But these patterns and using sidecars in order to take the information from the immutable world and put it into the mutable world, these patterns will be there for you to use forever. As soon as you start to apply them, you'll be able to continue to use them. You don't have to use them only as a stepping stone to immutability. So in the book, The Art of Immutable Architecture, I go through several of the patterns that I've used in order to integrate with stateful applications, RESTful APIs, databases. How I've used things like RabbitMQ and Kafka in order to take these immutable objects and turn them into messages. What are the patterns? What are the mechanisms you can use in order to translate from one to the other? And so I put this all together in a way that hopefully you can take this, you can apply this to your own applications. And now that you've got the incredible power of Kubernetes and the awesome capability of historical modeling, you can put those together and you can build some really awesome things. So I thank you very much. I invite you to join me on Twitter at Michael L. Perry and continue the conversation at immutablearchitecture.com.
We have a few questions too before we finish. The first one, I will show it on the screen. Have you had an opportunity to implement the historical model in production or use it in production?
Yes, very much. The application that I'm currently working on is in the healthcare space, and so this application is all about gathering volunteers that need to are physician assistants, nurses working in one area, and they want to be able to transfer their license to be able to volunteer in a different area, and so we're capturing each of those different events as an immutable record within a database, and so we're using a database literally as an immutable record with the foreign key relationships representing those predecessors. In addition to that, I've also built a couple of immutable runtimes now, and I'm using those in production in order to solve problems using a different tool chain that's intended to be used in this way. So when I talk about representing a historical fact as a JSON object, one of my immutable runtimes, Janaga, literally works that way, that you create a JSON object and you say, this is a fact. And then the Janaga runtime shares that with the server, that shares it out with other clients that are connected to that server, and it propagates that information. So yeah, I would say that at this point, it's my default architecture.
Oh, sounds good. Okay, so the second one. What do I miss? An explanation how you would apply this to a real system without automated conflict resolution, some consensus protocol.
Yeah, that is a really powerful point. In a lot of the systems that try to solve this problem, they will have a specific point within the application where all the information has to go, and then that server makes a decision. So it has an automated conflict resolution strategy that it employs, and then once it decides what the resolution is, then it pushes the results out. I call that using topology in order to solve a consistency problem, and I find that then causes additional problems. So if there is some central part of your application that that your decision has to make it to before then the conflict can be resolved, then you can't work disconnected from that part of the system. If you take a look at Git, Git doesn't do automated conflict resolution within your commits. It's up to a developer to do that, and so the developer can make the most important decision, and they don't even have to be connected to a specific remote in order to do that. They can share commits just machine to machine, peer to peer, and still achieve the same result.
Okay. So the last one, but similar. If you have more questions, just write them in the chat. If you prefer to write in Polish, just write in Polish. I will try to translate them in English. So the question, how to handle a situation where the request goes not to up-to-date node with the stale historical facts?
Yes. So, yeah, one of the Git is another great example of this. One of the problems that you might run into with Git is that we both commit two different branches, and then we pull each other's branches, and we both see, oh, there's a conflict, and then we'll both do a merge. And then if we try to both push our merges, we'll have continuing conflicts. If we were to take that same model and automate it, and not centralize it, so we're not using topology in order to make that a bottleneck and solve the problem, then we could have two servers out there that are competing with one another to come up with conflict resolutions. And so when I build a system using these concepts, I won't automate that conflict resolution at all. I will let the users take care of it. So you can present to the user the fact that there are two leaves of this directed acyclic graph. You could say, okay, here's your customer record. Now we've got a little red star next to shipping address, and it's got two fields in it. And you can say, okay, it's that one instead of that one. And now the user is creating that resolution fact, and it's going back into the system. So yes, that does mean that somebody else could resolve it in a different way, and they could end up competing with one another. But I'm relying upon the first of all, the fact that humans are slower than machines to
sometimes.
Yeah, sometimes, yeah. So that helps. But then also, after one round of that, people are going to call each other. And they're going to say, "Hey, wait a minute, I need to fix this." So I'm not trying to take away from the people involved their ability to solve the problem.
Okay. The next one. You mentioned to use some sidecar for translating data to database. Guess for immutable data, better to use some non-SQL database right away, and then you skip the translation. Is that correct?
Yeah, I would say that a NoSQL database can certainly help in this regard. That said, I have used relational databases as immutable databases as well. So it's really more to do with how you apply the tools than the tools themselves, at least right at the beginning. Like I said, I'm currently building tools that know that you're coding with an immutable architecture in mind, and so they have the constraints built in. But most of the NoSQL databases that we currently use don't have that constraint of immutability built into them. So you still have to constrain yourself. You still have to decide not to update information, not to delete information. If you're using a graph database, the graph database isn't going to prevent you from updating a record. So you have to prevent that yourself if you want to use it in that way.
Okay. So the last from me is Matt Smith, your favorite Doctor Who?
Yeah, honestly, so my daughter was a David Tennant Whovian. I am more of a Ken Baker Whovian myself. I like to go to school.
Okay, so if you have the last chance for questions, okay. So there's no questions. Thank you very much, Michael, for coming here.
Thank you so much. This has been a real pleasure.
And to all our listeners, remember about our action, Architektura I Kontenery. Pomagamy. If you can add even 10 zlotys, it will be great. Thank you for your presentation, Szymon. But thanks. Thank you very much from me. And that's the end. I will end this broadcast.